heterogeneous trust with probabilistic witnesses. Go ahead.
Hi, everyone. Thank you for staying for the last session. My name is Liron Schiff. I'm a researcher at Akamai. I'm presenting here joint work, and it's ongoing research, and this is our main results and some recent ideas. So this talk is about randomness, trust, and also money because of cryptocurrency. So just a funny anecdote, when you trust the randomness of the roulette, it's called gambling, but when you trust the randomness of a pseudo-random generator to connect your bank, it's called security. But don't worry, I'm not going to talk about gambling here. So cryptocurrency, and actually every currency, and actually this work also works the same for asset transfer. But the idea is that we want to keep a balance of multiple processors or peers over time. And these peers can make transactions where they update their balance. So for example, we can see here P1 transfer 10 to P2 and update. And as a result, both of their balance are updated. However, one of the security concerns in this kind of distributed, if it's a distributed system, is for someone doing double spending, like trying to use the same balance to do 2 transactions and for updating 3 accounts, for example. So this will lead to this kind of state, which we don't like. What we would like to do in this kind of cases is to enforce that only one of these actions will happen, maybe even to identify the ones who try to attack us and maybe block its account forever. So how we can do that? How can we prevent double spending and in general preserve the properties of such systems? So one kind of solutions is to have a shared view of everyone's balance. So in the classic solution, we have one centralized database, the bank, that just make transactions over this database. But in a more distributed cases, we usually use replicated state. This is what blockchain is providing us. However, it is already known that to manage balance in this way, you could use weaker objects like reliable broadcast. Reliable broadcast essentially means that we have several peers. When one calls a broadcast, we are guaranteed that every non-faulty will be able to deliver this message, like accept this, receive the message and accept it. And if they're in the faulty ones, we don't care what they do. But here I want to discuss about the multi-instance reliable broadcast. So usually reliable broadcast is an object that allows to do one-time broadcast. So in this case, we define the message as having, as containing both the origin, the one who created the message, or the owner of the account that make a transaction, as well as a tag and the value. The value is what actually is the operation, and the tag together with the origin defines an instance. So we, of course, can have multiple broadcast instances in our system. This is a definition of reliable broadcast. The fact that it's multi-instance is essentially, we can see it expressed in the consistency requirements, where if 2 peers receives a message from the same peer, with the same origin, and it also has the same tag, then we require it to be also the same value that is broadcasted, assuming they are non-faulty. Okay, so no one can send the same message with the same origin and tag, but with different values. Or we can try, but it won't be accepted by the non-faulties. Other requirements are kind of, I think, very intuitive. So it's known that we can only achieve that when the number of faulties are less than a third of the network. And then the complexity, the message complexity is n squared. We can see here illustration of the Braha algorithm, the protocol, but basically every node, every peer should make sure he try to contact all other peers in order to be certain that it's the property is guaranteed. So this gives us n squared. And as we said, it can also prevent the double spending and detecting other attacks. So the way to do that is that we use a tag, the instance, to track the index of the message of each peer. So in this case, the attacker P2 will have to send 2 messages, and they both should have the same tag, which also uses the index of the message that he sent. You should pretend both of them to be the first message, but they will have different values. But as we said, from the definition of reliable broadcast, only one of them will be accepted. Okay, so this is a basic implementation of cryptocurrency with reliable broadcast. But now we go over the message complexity, and we think we want to find a way to make it more efficient, so that we can do this in faster rates. And one direction is to say, what if we have trusted set peers that we know that will function good in a good way? And the idea is that, of course, if we have such a set, let's say the size is W, then the complexity becomes W times N. Because basically we just use this set of the witnesses in order to communicate with everyone else. So every peer should only communicate with this set, and it shouldn't communicate with all other peers. And here is an illustration of one of the protocols in our work. So it has several stages, but in each stage we either have the witness set communicate with all peers, or all peers communicate with the witness set. In any case, the complexity is W times N. But there are some challenges. If we want to do something like that, we need to know how to select this set. And we also, if you consider security, if this set is known in advance, then the attacker can make an effort to compromise it. And the idea that we explore in this work is to use random sets. So we randomly select a set for each message and transaction. So the benefit is, one very nice benefit is that if we look on the ratio of compromised node inside the random set, with high probability, it will be the same as the entire population. Also, it's unpredictable. So it's hard to compromise it in advance. So one way to do that, we could use some multi-party computation for a random shared random value between everyone, but this has high complexity. Another idea is to use blockchain blocks, so the hash of the last block as a random source, but this also requires a lot of synchronization about what is the last block. And there also have other assumptions. And our idea is to make, what our goal is to make a random selection in very high rate. So we want a more efficient way. Do you have any questions till now, what we are trying to do?
You one question?
Yeah.
So here you're trying to select the witnesses that everybody will agree on, or are there different participants will use different sets of witnesses?
So actually, this is answered right.
Oh, sorry.
The next slide. No, it's a good
ahead.
question. Yeah. So our idea is to use locally sensitive history hash. So we want to hash the idea is that each peer will hash the history as it knows, and even though they are not the same, they should be similar enough so that the outcome of the hash will also be similar. This is the locality sensitive hash. And then based on these similar hash values, we will also select similar witness sets, which has a lot of overlaps between them. Yeah?
Now I have to ask, why do you think it's a hash? Because you want to produce randomness. Practically, for the cryptographers, a hash function is not produce randomness.
That's right, if you know the input, right? But because the histories are changed as the outcome of all the operations of all the networks, this becomes a source of randomness to the hash. Okay. So, so the challenges are we have histories that can be a bit different for different peers, because maybe some of them didn't get the recent messages. Maybe they got these messages, but in different orders. We want the outcome to be hard to predict, at least not very far in the not in advance, not in short time. So, I mean, you don't want to predict now the hash that will be in an hour. If it just the immediate hash in just 1 minute, you won't have enough time to attack and compromise it. So our solution is to use the history, to hash the history into a vector that in a cyclic d-dimensional space. It's often called a torus, so that it's cyclic in each dimension. And every time we get a message, we hash it to obtain the index of a dimension and a direction, up and down. And then we update the vector in this dimension, and we add it the change in the same directions that we selected based on the hash. And this in the same hash space, we also hash the IDs of the peers. So once we want to select a witness set, we look at the current hash value of the history in this space, and we select all the witness sets, all the peers that are the closest to this point in space. So we can consider this as kind of a random walk in the torus, where the peers are uniformly scattered, and then based on the messages that are added to the history, we have a random walk in the space. And when we need to select a set, we see which are the nodes that are most closest to the point where we are in this random walk. We also have some extensions to make it harder to predict, where for each, we actually run a random walk for each of the peers' IDs. And then, so even if the attacker could select the IDs to be together, they could, after some time, it's hard to predict where they will arrive. So it's hard to make all of them to be selected at the same time, so that all of them will be close to some point. It's something that will be hard to predict. We have much more details in the technical report, which you can see. I try just to give a kind of overview of the results. But now we can ask, can we trust these witness sets? So in the paper, we define a probabilistic variant of the reliable broadcast definition. And we can show that they are provided with high probability. In general, we can say that when the random set is selected, the probability that it will be compromised is very low. Yet, of course, it depends on how big is the witness set. The bigger it will be, the more secure it will be. And also about how much differences there are between the different nodes, because as the differences become bigger, the witness sets that each select will not overlap. Will be less and less overlap. Also, we can see that if the attacker just waits till something miraculous will happen and all of its nodes, compromised node, will just be together and selected, this can take very long time, so long that it was very hard for us even to simulate and predict when the parameters are big. And other things that maybe I can stop here if you have questions before we go to the next point. But the idea that, if I just summarize for now, we showed how we can select a set that could be trusted from in many senses. You want to ask?
Maybe a quick question. So if I'm a participant in the system, I look at my received message history. So this is the walk, and I translate it to a walk on the torus. And then I look at the points next to me in that torus.
Next to this
Next to
value
where
of the random walk, current random walk value.
And so if I look at a different participant, maybe the history is slightly different. And is there a guarantee that the random walks nevertheless are kind of close to each other? Or
Yeah, if the histories are similar, then they should. So all the locations should be close to each other.
Okay.
So next, we wanted to think of, okay, in addition, we know how to select this random set. Let's say we also have some external source of trust. Can this be combined together with this random selected set? So one idea we have is to adapt the witness set size based on the of the one who issued the message. So let's assume that the trust is kind of the probability that someone will try to do double spending, okay? And as I said, by using different witness set size, the protocol will take more time to verify, but we also get better probabilities or smaller probabilities that an attack will happen and we won't catch it. And the probability that everything will fail is the probability that someone will try to attack times the probability that if it attacks, we won't detect it, which depends on the size of the witness set. So we can make sure that the more we trust someone, then the smaller witness set we will use and make things faster. And keep the multiplication of these two probabilities constant. And this will allow us to have faster transaction within trust clicks, because I trust everyone inside, we use smaller witness sets, the verification is faster and we can progress faster. Another idea is if we have like Boolean trust, so that everyone, there is some peers that it trusts and some that it doesn't. And what we can actually show is that most of the time, assuming a logarithmic size witness set, and assuming we have a very high rate of trust, so that everyone trusts some portion of all the peers, then most of the time the random set will also contain for each peer someone that it trusts. And even if we consider that it needs to add some peer that it trusts to the witness, to the random set, it won't happen very often. And the total number of peers that will be added by different other peers is constant. Yeah, this is what I mentioned. It all depends on the parameters you select, but for example, if C equals 10 and everyone trusts at least 10s of the peers, then the random set will very likely to be always contain a trusted peer for every peer, and the number of added peers will be constant. So in summary, we discussed about cryptocurrency using reliable broadcast. We show that we can have low-cost reliable broadcast using trusted witness sets. And we saw how we can select random witness set using this local sensitive hashing of the history. And we also saw that we can use external source of trust. Yeah. Yeah, I also felt that I need to mention this thing that happened in Israel. I don't live in Israel now, but many of my family and friends are there. So thank you.
Can I ask, you have this random walk on the torus. How important is it to use the torus versus some other topological shape?
Instead of what? Sorry.
I could use the torus. Maybe I could think about using some other high dimensional shape and doing a random walk on that.
I guess you can, but we wanted something that is very simple and also easy to hash IDs into it as well.
Thanks.
It's also very symmetric from all point of views.
So what happens if you use a sphere?
So the face of the sphere is also, I think, is kind of the same, right? So the torus. So the torus is just the name I found that matches this. But you see, there are multi-dimension, and each of them you can overlap. In the sphere, I think you overlap differently, and so there is dependency between the different dimensions. Here, they are independent.
Okay.
This approach of sampling like a random witness set, how is that different from just like having random leader election or like protocols that proceed in views with different random leaders?
I'm not sure whether it's the complexity of leader election, and also if it's regarding the guarantee, how much it's reliable.
I guess one way is it fair to say that this is a protocol that behaves like electing more than one leader, because the role of the leader is kind of limited in this protocol?
Yes, and we also don't require them all to be synced. You can run it without any communication between them. So we just use the messages that already received as part of the history. There is no extra traffic required in order to select the sets. In either election, you will need to exchange messages.
No, I guess blockchains usually elect next proposer based on also hashes of the history so far, right?
Yeah, but then you need to be synchronized regarding what is so far, where you stop the so far. You need, it's much more synchronous in this sense. If you add more, if one of them see one more block and they think this is the last block, then it will be.
But there'll be some stable history of it, right? Some part of it is at least is stable because that's the security of the.
Yeah, you need to.
Anyway.
Yeah, but so you need to be defined. You need more guarantees about the synchrony. What messages, where you stop, how the history looks like, and which message you consider when you do this random selection.
Okay, and if you have time for one more, what can you say about the unpredictability of the witness selection?
Yeah, so one of the things we try to analyze is how many messages you need to insert in order for this to be completely random. It's called the mixing time of the random walk. And this thing is, we try to control it by also looking on the rate of messages. So the higher the rate, the faster it will become uniform from any point of time that you know what it was. So this is the kind of thing we look at the analysis.
Any other question? I guess we still have 5 minutes, so if I may ask another one.
Sure.
So I didn't understand exactly why small differences in history lead to small differences in the random walks.
Yeah, so I take the simpler version, okay, that we have only one random walk, okay, let's take for this. So the points are fixed, the IDs are mapped to some point in the space. Now you walk inside, and if the hash is similar, then your point is also the point you're inside. It means that you also map to close point in the space. And if you take the proximity in this space, you also have similar points falling in this proximities. So let's say you take the radius of 10 around the point. If these 2 points are very close, then similar points will fall in these 2 circles if it was like 2-dimensional plan.
Okay. Okay, I'm starting to get some intuition about that. I need to read the paper, I guess. So maybe if I may rephrase something, so the main difference compared to something like Algorand, where they also elect a random committee, is that so in Algorand there is some kind of agreement on what information to use to sample the system, whereas here you don't need this hard agreement on the information you're using. You just use your local history.
Yeah. Yeah. One more difference is that Algorand consider a stronger attacker which he can, if we map it to here, it's like it can compromise in a flipping of a second the selected
Yes.
witness set, and while we assume it takes some time, enough time that the random walk can progress and
Yes.
select another one.
Cool. Thanks.
Thank you.